Hey, what's going on, guys? Let's do this problem right here. So we have a house on top of a hill that is 100 meter above from the ground. At this point we have the pressure 2 atm, and they are asking for the P1, the pressure in this big pipe right here in the bottom, right? So let's see how we can calculate this one. So we are going to use the Bernoulli equation to find that. So let's use the Bernoulli equation, that is P1. I'm using the pressure equation. P1 plus rho g y1 plus half rho v1 square is equal to P2 plus rho g y2 plus half rho v2 square, right? So this is the equation we are going to use, and since this is a big pipe, we can neglect the velocity right here. So velocity v1 is going to be equal to 0. Then these are v2 values, right? v2 values. The first condition is when pipe is closed, like the velocity on the top is 0. So if we already say this is negligible, so we can cancel this one, and this is v2 is equal to 0 when the pipe is closed. So this is also be cancelled, and the further one is the height is 0 because we are taking this one as reference point. So this is going to be 0. We can cancel this one, these things, and we are left with this equation. P1 is equal to P2 plus rho g y2, right? Rho g y2. Then we have the P2 is provided 2 atm. This one we can plug all the values. So here the rho is going to be water. This is water pump, right? So water pipe. So it's going to be density of the water 1000 kilogram per meter cube times 9.81 meter per second square. Then we have this y1, that is and y2, that is this height 100 meter, and that's all we have. So this is going to give us the Pascal value. So let's see, 2 atm, and if we plug this value in calculator, that gives us 980. So I take this one as 80. So 980,000 Newton per meter square, and one atm is 101,300, right? 1 atm is equal to 101,300 Pascal. So we can convert this one into atm by dividing this value by this value, right? So if I divide this value by this value, that gives us 2 atm plus this is going to give us 9.67 atm, and that is equal to 11.67 atm. So this is the pressure required here to push this water from here to the top when the velocity is equal to 0. So let's see what happens when we have this velocity. So what's going to happen is this other side is going to be same, right? But here we are going to have a v2 value right here. So that's going to be the new change. We can say the delta p. That's going to be the delta p. So delta p, if we calculate this value, that's going to give us the difference because we already know these values that is here. So let's calculate delta p, the new change. That's going to be equal to only this dynamic pressure, the new dynamic pressure, that is half rho v2 square. So half times rho is 1000 times this v2 is provided 1, so 1 square, that gives us 500. This is just 1 square, not 1000 is not in the bracket, right? So 1 square, then that is going to give us 500 newtons per meter square. So that is a new pressure change when the velocity is like when the pipe is open or something, right? So this is B part, this is A. Then let's do the C part. When the velocity of this pipe, whatever the tap they are opening, that's going to be 5 meter per second. So delta p we can cover. Delta p is equal to half rho v2 square, same thing. It's equal to half times 1000 times v2, that is 5 square, and that gives us 500 times 25, right? This is 25, so 500 times 25 is going to be 12,500 Newton per meter square, and that's the new pressure change, and the velocity on top is 5 meters per second, and that's how we do that. I hope you guys like this video. See you next time.